Hi there! Welcome to Water Treatment Training at wttraining.com. In this webinar, I will be introducing you to the first topic of the wastewater treatment series. Here, you will understand the basic concepts related to water and waste treatment before we go into a more detailed approach of each of the treatment process steps. This presentation will also help you understand the process of treating influent water and wastewater, setting up control measures to maximize the effect of treatment programs, and as well as to maintain safe surroundings and environment. First, we need to know what is the definition of influent water, wastewater, and effluent water, as I will be using these terms a lot during the course. Influent water is essentially all the water that flows into the plant to be used in its industrial processes. Influent water may come from town's water, underground bore water, or river water. It may come from anywhere, but it has to meet the purity specifications before use. Wastewater, on the other hand, is all the water that has been used by industries for industrial operations. This water is usually highly contaminated and contains high levels of dissolved or suspended matter. Wastewater needs to be treated and purified to meet the safety regulations before it is discharged into sewage and streams. This discharged water can otherwise be called effluent water. There are many reasons to which we need to treat water and wastewater. Firstly, it is to have good quality influent water. Many industries requires good quality influent water to avoid contaminations with the processes and to avoid process equipment damages. After water has been used in the industry, impurities in the wastewater must be removed before the water is discharged. The effluent water must not contain any more than the permissible limits for impurities before it is being discharged. Without proper treatment, the wastewater will pollute the water body it is being discharged into, as wastewater may contain high levels of hydrocarbons and chemicals. Many of these substances are toxic, poisonous, or even carcinogenic. Without proper treatment, contaminated water will harm marine life and eventually affect all life forms. There are also situations where wastewater is treated not only to a quality that is safe for the environment, but to a higher quality that is fit for use by the manufacturing processes. This enables the manufacturing plants to conserve water by reusing the treated water. In some countries, where the water resources are scarce and the water price is high, many industries are driven to look at some new ways to conserve and recycle wastewater. It is important to recycle wastewater to ensure continuous running of the plant at the desired capacity. In certain industries, contaminants in the wastewater may be of high-value materials, such as the gold in wastewater from the gold plating plant, or the oil in wastewater from oil refineries. It makes sense to recover these contaminants from the wastewater stream as much as possible. If these precious materials are not recovered from the wastewater, high wastage may occur and profitability could suffer. There are mainly three types of contaminants in wastewater, in which we'll deal with each one differently. Suspended solids are particles that do not dissolve in water and can be seen with the naked eye or through an ordinary microscope. They contribute to turbidity and can be removed quite easily by using physical or mechanical means, such as sedimentation or filtration. Dissolved solids is a measure of total amount of dissolved matter determined by evaporation. Various softening processes, such as lime softening and cation exchange via hydrogen zeolite, will reduce dissolved solids. Colloidal suspended solids are solids that are not truly dissolved and yet do not settle readily. These are somewhat loosely defined as the differences between the total suspended solids and the settleable solids. There is at present no simple or standard laboratory test to specifically determine colloidal matter. Most colloids will not settle out even after long quiescent periods of settling. Many colloidal particles remain suspended in wastewater because of their small size and electrostatic repulsion. Electrostatic repulsion is the mechanism that controls particle stability. At the interface of the hydrophobic surfaces, excess anions or cations may accumulate. With hydrophilic surfaces, surface charges exist and it attracts ions of the opposite charge of the surface. The electrostatic and van der Waals forces strongly bind these ions to the surface. The layer of accumulated ions at the surface produces an electrical potential that repels particles from each other and causes the particles to remain suspended in water due to mutual repulsion. So, The negative surface charge, together with van der Waals force of attraction, develops a layer of ions next to the particle surface and builds an electrical potential, which prevents particles from agglomerating into larger particles. When lemon juice is added to milk, the stable particles of milk destabilizes and curdles. It now coagulates to form cheese. In influent or wastewater treatment, coagulation is used to chemically increase the size of the particles so that impurities can settle out faster. Particle size is built by neutralizing the negative surface charges on these particles. Initially, the layer of ions or charged molecules accumulate at the particle surfaces and create the electrostatic potential. When the negative surface charges are neutralized, the electrostatic potential diminishes and so does the electrostatic repulsion. Now, the particles agglomerate naturally. Cationic polymers and inorganic coagulants can be used to neutralize the surface charge of these particles. Self-precipitating polymers not only neutralize the surface charges, they also link particles together with their long-chain molecular structure. As the long polymer molecules sweep through the solution, they catch more particles and binding them together to form the sweeping flock effect. This, therefore, serves a dual purpose of coagulant and flocculant. I will cover more about flocculation soon. All of these three balls are made of the same material and hence have the same density. When the balls are released, which of the three balls will travel faster down the tube? Have a guess. The speed which the balls travel down the tube of liquid is known as the settling velocity. It is determined by the size and density of the balls. Similarly, in solid particles in wastewater, have a settling velocity that is governed by the Stoke's law. According to Stoke's law, bigger and denser particles travel and settles down faster than smaller and less dense particles as they fall through a fluid under gravity. This is the formula expressing Stoke's law. The settling velocity of a particle is directly proportional to the square of the particle's diameter. The settling velocity is also directly proportional to the difference of the densities between the particle and the fluid that it is in, although the settling velocity is inversely proportional to the fluid's viscosity. However, at this point, you only need to look at the concept of particle size, as the particle size is something we can chemically influence. Note that, as the particle size doubles, the settling velocity will increase to 4 times, and as the particle size triples, the settling velocity will increase to 9 times. Hence, increasing the particle size is an efficient way to improve the separation of the impurities, and this can be achieved easily by coagulation. There are 2 types of coagulants, the inorganic salts and the organic polyelectrolytes. Inorganic salts of aluminum or iron neutralize the charge on the turbidity particle. These also hydrolyze to form insoluble precipitates which entrap additional particles. With the exception of sodium aluminate, all common iron and aluminate coagulants are acid salts which lower the pH of the treated water. So depending on the initial raw water alkalinity and pH, an alkali, such as lime or caustic, must be added to counteract with the pH depression of the coagulant. Organic polyelectrolytes are mainly water-soluble that can be used alone or in conjunction with inorganic coagulants. They are water-soluble organic polymers with numerous ionized sites for both coagulation and flocculation. Now let's compare the 2 types of coagulants. Organic coagulants have some advantages over inorganic coagulants. Organic coagulants create a smaller volume of sludge. This means the sludge disposal cost is lower with organic coagulants. Secondly, unlike inorganic coagulants, the performance of organic coagulants is less pH dependent. Hence, operationally, it is easier to operate without having to closely monitor and control the pH. Most of the inorganic coagulants, except sodium aluminate, have low pH, which makes it less safe to handle. Also, the equipment needs more maintenance due to corrosion. On the other hand, organic coagulants are weakly acidic, much less acidic than inorganic coagulants. Additionally, Organic coagulants are biodegradable and hence are more environmentally friendly. Although the unit prices for organic coagulants are generally much higher than inorganic coagulants, the dosage requirement for organic coagulants is typically 10 to 20 times lower than that of inorganic coagulants, and the overall cost may still be lower by using organic coagulants. Even if the overall treatment cost with organic coagulants is higher, its use may still be justifiable with all the other benefits. However, the final choice of coagulants would depend on customer requirements. After coagulation, the coagulated particles will come down together to form larger lumps. This process is called flocculation. Flocculation is a method to chemically increase the size of the coagulated particles so that impurities in the wastewater settle out. During flocculation, the physical interparticle bridging mechanism relies mainly on the size and structure of the flocculant molecule rather than its charge density. High molecular weight polymers work primarily via interparticle bridging. Polymers of long chain and branch structure increase the efficiency of the flocculation. Selecting the right flocculant is greatly influenced by its molecular structure, charge, molecular weight, and form. With the advancement of technologies, the manufacturing of polymers that have precise placement of charges are possible. The optimum spacing between the charges ensures that all charge sites are used and that expensive charge is not wasted. Different molecule structures have its use for a range of unique applications. Polymers might have different charges, either cationic, anionic, or non-ionic. The charge density of different polymer molecules may be different. For contaminant particles that have a low charge, you need flocculants of low charge density, and vice versa. Molecular weight affects the selection of the flocculant. Flocculants have different molecular weights ranging from low, medium, to high. The molecular weight indicates the size of the polymeric molecule. A large molecule tends to do a better job in interparticle bridging mechanism. Polymers are available in 4 different forms: powders, liquids, emulsions, and dispersions. Powder forms are highly concentrated. Emulsion polymers are composed of water, polymer, and oil. Brine dispersions are cationic flocculant liquid. Powder emulsions tend to have higher molecular weight. Powder is the most concentrated form of flocculant. It is the most expensive on a unit price basis, but it is the least expensive to use. However, it is difficult to feed. It requires a special Makedown or chemical mixing system. It is available as a high molecular weight cationic, anionic, and non-ionic polymer. There are 2 methods to make down a dry polymer powder: manual and automatic. A manual makedown system consists of a makedown tank, an eductor, an agitator, a feed pump, and a calibration cylinder. A feed tank is optional but advisable. If a feed tank is available, it should have an agitator running continuously at low speed. This will keep the makedown solution homogeneous. When the feed tank is used, a transfer pump is required, and this must not be a centrifugal pump as it will degrade the polymer, resulting in poorer performance. The dry powder polymer is introduced into a mixed tank through an eductor with water. The eductor ensures that the polymer particles are wetted properly. The agitator must not run any more than 350 RPM and normally for no more than 30 minutes. Once the solution of dry polymer becomes clear and the polymer is fully dissolved, the agitator should stop. The solution could then be transferred into a feed tank if there is one. This gradually reduces the solution level in the mixed tank and increases the solution level in the feed tank. An automatic power feed system is expensive. However, it allows hands-off operations and ensures consistent makedown quality. In the automatic makedown process, the polymer is fed from the helix feeder. It is evenly distributed over the rotating drum through the spreader. The thoroughly wet polymer is then brought to the eductor in the state of suspension. When the polymer is added to the mix tank through an eductor, the mixer starts rotating. The polymer is then totally mixed and the transfer pump starts pumping. The polymer is then fed to the point of application. Here are some tips on handling dry powder polymers. First of all, dry powder polymer needs to be stored in a low humidity environment. Otherwise, it may absorb moisture from the air and becomes caked up. For the same reason, containers of dry polymer should be sealed with cover. The Makedown polymer solution should be consumed within 24 hours after preparation. That is why the feed tank is normally sized for 8 to 24 hours capacity. An eductor is used for powder transfer to ensure that the dry powder polymers are individually wetted. Otherwise, undissolved polymer globules, commonly called fish eyes, may be formed. The maximum solution strength for an ionic dry polymer should not be more than 0.5%, and for cationic dry polymers, it should not be more than 1%. We can further dilute the solution to a lower concentration for better performance with an inline mixing arrangement. Liquids cost more than powders, but are much easier to handle. You may need to dilute it to feed it in. In many cases, it can be fed neat without dilution. It is usually available as a cationic low molecular weight material with high charge density. The liquid polymer may be injected neat into the water treatment processes. However, for better mixing effect or better pumping rate at convenient strength, it can be diluted in batches or to an inline mixer. A batch dilution system for liquid polymer is normally used for high viscosity solution. The system consists of a tank, an agitator, a feed pump, and a calibration cylinder. A feed tank with a transfer pump is optional. The liquid polymer is added to the dilution water in the mixed tank while the agitator is running. Once the dilution is homogeneous, the agitator should stop. The solution could then be transferred into a feed tank if there is one. In the inline dilution process, a metering polymer pump is used to feed neat undiluted polymer solution into a dilution water line where an inline mixer is installed. The inline mixer creates turbulence to ensure good mixing of the concentrated polymer solution with the dilution water. There are also some special precautions that should be taken with respect to the handling of liquid polymers. The liquid polymer should be stored at moderate temperature between the range of 60 to 120 degrees Fahrenheit or 15 to 50 degrees Celsius. It is important to protect the polymer from freezing, because some polymers can suffer irreversible damage when frozen. Liquid polymer solution does not require periodic mixing to prevent separation before use. However, some liquid polymer solutions have a short shelf life. Hence, inventory should be well planned accordingly. For high viscosity polymer solution, the dilution should be 20% or less. A further 10 to 1 dilution with an inline mixer would be a good practice, especially for sludge dewatering applications. Always try to avoid making down more than 24 hours supply. Emulsion is another type of flocculant that has a higher concentration than the liquid form. The polymeric molecules are encased in fine water droplets that are in turn emulsified in a continuous oil phase. Before a molecule can serve its purpose, it needs to be activated from the water droplets to open up the molecular structure. To activate a molecule, it requires an inversion process and needs a special Makedown or chemical mixing system. The polymer molecules are initially coiled within very fine water droplets in a water-in-oil emulsion, where the water is dispersed in the continuous oil phase. During the Makedown, a lot more water is added, and agitation action breaks the oil into fine droplets. The emulsion turns into an oil and water emulsion where oil is dispersed in continuous water phase. As a result, coiled polymers uncoils in the continuous water phase. The batch Makedown system for emulsion polymer is exactly the same as that for the liquid polymer. The system also consists of a tank, an agitator, a feed pump, and a calibration cylinder. Except that it is important to have the feed tank, as it allows time for the inversion process to happen. In a batch Makedown system, the feed tank should have an agitator running continuously at a slow speed. This will ensure homogeneity of the Makedown solution. Use diaphragm pump for transferring polymer solution from the mixed tank to the feed tank. The emulsion polymer is added to the dilution water in the mixed tank while the agitator is running. Once the solution is homogeneous, the agitator should stop. The solution could then be transferred into a feed tank. A continuous Makedown system uses a float valve to control the water supply. The flow of water supply in turn activates a flow switch to turn on the pump that transfers emulsion polymer from the chemical storage to the chemical tank. This automates the Makedown process. Whenever the liquid level in the chemical tank is low enough, the float valve initializes the automation cycle. The chemical tank itself provides the resident time for the inversion process to happen. The polymer solution pump delivers the Makedown polymer to the application point. Where necessary, secondary dilution can be made using an inline mixer. Here are some precautions that you need to keep in mind when handling emulsion polymers. It is important to store the neat emulsion polymer in a low humidity environment. Also try to protect the storage drum from having condensation inside the drum because a small quantity of water can cause the emulsion to gel up. Like dry polymer, it is best stored at a moderate temperature range of 60 to 120 degrees Fahrenheit or 15 to 50 degrees Celsius. During the Makedown process, the initial Makedown strength should not be more than 1 to 2 volume percent. For best performance, a further dilution to 0.2 to 0.5 volume percent is recommended. Like other types of polymers, avoid making down more than 24 hours supply. If Makedown stock has been standing still for some time, always mix before use. Remember, always add polymer to water while agitation action is on. Adding water to polymer would gel up the polymer and it will not be possible to dilute it further. Brine-based dispersions are available as cationic flocculants. The Makedown for this form of flocculant is fast and easy. It only needs to be diluted with water. However, dispersions need to be mixed periodically in bulk storage to prevent separation and gelling of the product. According to the dispersion model, the initial form of dispersion is a brine solution of individually coiled polymers, each being stabilized with some surfactant or stabilizer on its surface. This stability is maintained by high salt concentration. That is why dispersion polymers are kept in brine solution. When the polymer product is diluted, the salt concentration surrounding the dispersed polymer particles reduces significantly. As a result, it is difficult to keep the surfactant on the particle surface. This causes the polymer to slowly open up. The batch dilution system is the same as that for the liquid and emulsion polymer. The system consists of a tank, an agitator, a feed pump, and a calibration cylinder. A feed tank with a transfer pump is optional. The brine dispersion polymer is added to the dilution water in the mixed tank while the agitator is running at no more than 350 rpm for 10 to 20 minutes. Once the dilution is homogeneous, the agitator should stop. The solution could then be transferred into a feed tank if there is one. The inline dilution is also the same as that used by any liquid polymer solution. A metering polymer pump is used to feed neat undiluted brine dispersion polymer into a dilution water line where an inline mixer is installed. The inline mixer creates turbulence to ensure good mixing of the concentrated polymer solution with the dilution water. Here are some tips that you need to keep in mind when handling a brine dispersion polymer. Firstly, it should be stored under a moderate temperature range of 40 to 90 degrees Fahrenheit or 4 to 32 degrees Celsius and be protected from condensation. The initial Makedown strength should be 0.5 to 5 volume percent. Further dilution with inline mixer to 0.3 volume percent is recommended for better performance. Before use, the neat product should be agitated or recirculated for 30 to 60 minutes to ensure homogeneity. It is recommended that the dispersion polymer storage tank be slowly and continuously mixed. As the polymer is brine-based, it is corrosive. Hence, carbon steel or copper alloy should be avoided as material of construction in the feed system. Suitable material for a tank piping and pump are high-density polyethylene or rigid polyvinyl chloride. Natural rubber, Buna-N, or Teflon may be used for tubing material. The high-speed rotation action of a centrifugal pump can degrade the polymer, so it should not be used for chemical transfer. Gear pump or diaphragm pump is recommended. Mixing is an important operation in the coagulation and flocculation processes, which directly affect the treatment performance. Initial mixing intensity is critical to accomplish optimum polymer dispersions and polymer-to-particle contact. Coagulation and flocculations are done under different mixing conditions. During coagulation, fast mixing is required for coagulant distribution. This is because turbulence created in the mixing operation increases the polymer-to-particle contact. In case of flocculation, slow and gentle mixing is required to encourage particle-to-particle contact. If the mixing during flocculation is too fast, the aggregates that are already formed will break up. Performing a jar test is important to stimulate the conditions of the plant and to determine the mixing rate. The jar test is recognized throughout the water industry as the most valuable and most commonly used tool for realistically stimulating coagulation control at a full-scale treatment plant. This test is routinely performed by water treatment plant operators as well as consultants and researchers. It basically involves duplicating sequentially in a single vessel conventional treatment steps that occur simultaneously at different locations in the plant. The jar test is a standard laboratory simulation for wastewater treatment and influent clarification. Jar test is used to determine the optimum chemical program, establish the best order of chemical addition, establish the approximate chemical dosage, and it is also to determine the best equipment operations, such as the most effective mix cycle for a given chemical program. While performing a jar test, ensure that the wastewater samples used in the jar test are representative or untreated samples. Hence, the water samples should be collected from the upstream of the chemical injection point. In addition, ensure that you vary only one parameter at a time while testing. You should not vary the chemical and mixing rate at the same time. You should simulate the same mixing sequence in the plant. In other words, if the polymer is first mixed to a certain length of piping and then through a mixing tank, and thereafter further mixed through another length of piping, then you should determine the mixing energy in each of these three mixing modes separately. Jar testing is used to evaluate the effects of changes in chemical doses and point of applications, choosing alternative coagulants, adding polymeric coagulant aids, implementing alternative pre-oxidation strategies, varying mixing intensities and times, and changing overflow rates of the removal of particles, natural organic matter, or other water quality parameters of concern. The key parameters include velocity gradient or mixing intensity in the rapid mix and flocculation basins, effective retention times in the rapid mix and flocculation basins, surface loading rate of the sedimentation basin, and actual retention time in basins if jar testing is being done to evaluate time-dependent reactions for which full-scale reaction time influences results. The intensity of mixing is generally quantified by the velocity gradient g, with units of seconds to the power of -1. The velocity gradient is calculated using the energy dissipation rate in the fluid, or it can be interpolated from the calibration curves. In order to attain jar test results that are relevant to the treatment plant, mixing intensities and therefore velocity gradients during jar tests should correspond to those in the treatment plant. The mixing speed of the jar test is expressed in RPM or revolutions per minute. The mixing energy varies for coagulants and flocculants. The appropriate mixing energy of inorganic coagulants is 200 to 300 per second of velocity gradient, 300 to 400 per second of velocity gradient for organic coagulants, and 60 to 90 per second of velocity gradient for flocculants. The jar tests help you determine the flocculant that can be used under specific conditions. For this flocculant jar test, you need to first fill a jar with a fresh sample of water and then mix rapidly at a speed that duplicates plant conditions. After that, you may need to chlorinate the water if this is practiced in the plant. This is an optional step and is based on the plant's operating conditions. Next, you need to measure the water pH with a pH probe while the mixer is still running. You may need to adjust the water pH with drops of acid or caustic to the actual plant pH or to the desired pH level. This pH adjustment is needed if there are pH adjustments at the plant and your water sample is collected from the upstream. In jar tests for investigating the impact of various pH, this is especially important. Some inorganic coagulants can lower the water pH significantly. In such cases, the water pH should be adjusted higher such that the final pH will fall within the desired range after coagulant addition. For practical purposes, the amount of caustic agent needed for pH adjustment can be predetermined by separate titration tests with coagulant added. Now add the coagulant to the jar at the desired dosage. The coagulant should be pre-diluted to the same strength as practiced in the plant or to a strength if you would like to investigate its impact on the treatment performance. Now the mixing of the coagulant starts. Keep the mixing running at the original high speed for the duration that simulates the mixing of the coagulants in the plant. At this stage, tiny pin flocks should start to form if the coagulant is effective. After the mixer has run at a high speed for the required duration of time, reduce the agitator speed to 40 to 50 rpm and add the flocculant. The flocculants should be pre-diluted to the same strength as practiced in the plant or to a strength you would like to investigate its impact on the treatment performance. After you have added the flocculant, immediately reduce the speed and run for duration that simulates the mixing of the flocculants in the plant. This is usually 20 to 30 rpm for 5 to 10 minutes. During this stage, if the flocculants work effectively, you should see flocks starting to grow in size. Stop the mixer and record the flock size and settling rate for each jar. The flock size is normally recorded as a comparative scale of 1 to 5, with 1 being the worst and 5 being the best. After 5 to 10 minutes, draw some water from the bulk and measure the supernatant turbidity. This process is normally carried out in 4 to 6 jars in parallel at the same time. Test different flocculants first to select the most effective one. After the most effective flocculant is selected, vary its dosage to determine the minimum dosage requirement. You may also evaluate combinations of different amounts of coagulants and flocculants to determine the most economical combination. In these tests, you may want to add the present plant treatment amounts to establish the first jar as a control sample. Other studies with jar tests may also be carried out to assess the impact of different pH, different mixing energy, or different temperatures on the treatment performance. Remember that you should only vary one parameter at a time. Now that you know the various types of contaminants and wastewater and how to deal with it, let's have a look at the most common treatment programs. Influent water clarification uses processes such as coagulation, flocculation, clarification, and filtration. Influent water clarification ensures that influent water meets purity requirements before it can be used in industrial process. Coagulants and flocculants are commonly used to aid the clarification processes. Similarly, coagulants and flocculants are typically used to improve the efficiency of the sedimentation and flotation processes. Wastewater treatment also commonly involves the removal of heavy metals. We have now reached the end of Introduction to Wastewater Treatment module in Wastewater Treatment series. Thank you for listening and watching this webinar. If you think you got value out of this webinar, please feel free to share this video to your friends and colleagues. Thank you very much again, and I look forward to seeing you again in the next webinar. Bye!